All right, hi everyone. This is part 3 of zk-SNARKs. Today's outline, we're going to review what we had defined 2 weeks ago, which is the definition of a SNARK. Then we're gonna go through 2 more examples of how SNARKs are used, and then we're finally gonna get to the mathematically intense part, which is to build a SNARK based on all the use cases we've heard of based on our definition. So reminder, when we had defined a SNARK, we had broken it down into, we've broken the acronym down into these words. It's a zero knowledge, succinct, non-interactive argument of knowledge. We had talked about what each of these means, like how knowledge is comprised of a public instance, X, and a private witness, W. And there's 2 parties here. There's a prover, P, who knows both of them. But then there's a verifier who only knows the public information. And so the witness, W, is something the prover needs to be able to argue. So I can skip this part, but the knowledge here, W, the prover wants to prove to the verifier that they know. And to formalize this, we have an arithmetic circuit here called C, which takes as input both the public instance and the private witness. And then formally, we want the prover to show the verifier that they know such a witness so that this arithmetic circuit evaluates to 0. The reason this is non-interactive is because the communication has to go in one way. So only the prover gets to talk to the verifier. The verifier does not get to talk back to the prover. So there cannot be a dialogue between the two. That would be too expensive on the blockchain. So we want the argument of knowledge to be non-interactive. And then when we formalize this, we can substitute like the prover and the verifier with algorithms. So the prover becomes an algorithm that takes in as input X and W and produces this proof, which is just a string. The proof is like a string. The verifier accepts the string along with the public instance and then outputs either yes or no, whether they believe the prover or they do not. And so you can sort of see an illustration of this system right here. The prover accepts as input X and W, and then this SP we're going to define in a second. It produces a proof that the verifier accepts as well as the X. And then this thing will also cover in a second. And then the verifier ultimately decides, all right, do I accept or do I reject this proof? And here, the S we can define as a setup algorithm. So a third algorithm, in addition to prover and verifier, the setup algorithm just produces some setup information based on the circuit, based on the argument we're trying to prove. And this setup algorithm will then produce 2 strings, one for the prover and one for the verifier, which is what you saw on the previous slide. This is the string for the prover, and this is the string for the verifier. The setup usually is just randomness. Typically, the setup just produces some randomness and shares it with the 2 parties. The reason why they have to share a different string with each prover and the verifier is because depending on the setup, sometimes it's very, very important that the prover does not see the randomness that the verifier receives. Otherwise, the prover can cheat. So then we just take this as a third input to the prover and to the verifier, and this becomes our formalized system for this argument of knowledge. And so there's 2 properties again that we talked about last time. They're pretty intuitive. The first one is that if there is a valid witness such that this circuit evaluates to 0, then when the prover uses this witness to produce a proof, the verifier must say yes. It's pretty straightforward. It means that if the prover is honest, the verifier should cooperate and say yes. The second property the proof system has to satisfy is proof of knowledge, which simply put down here is that if the verifier does not know a witness and the verifier, if the prover does not know a witness and the prover tries to produce proof, the probability that the verifier says yes to this fake proof has to be less than epsilon for some very, very small epsilon. So it's saying that the adversarial prover or a fake prover cannot convince the verifier that that their proof is correct. So these 2 are basic properties. Then we get to some runtime properties, which is the part that makes a SNARK hard. A SNARK is difficult because it has to be very short and succinct. There's 3 constraints here. The first is that the prover has to run in almost linear time in the size of its circuit. The proof length has to be at most log the size of the circuit. And then the verifier has to run in at most log the size of the circuit. And so as a quick refresher, there is a way we could produce a non-succinct proof the easiest proof you could make if you were the prover is to just say that the proof is equal to the witness. You just send the witness to the verifier. The verifier says, okay, I see that you have a witness here. Let me plug the public instance X and this witness W into the circuit and then evaluate it, and then it'll turn out true always, right? My question to people here, volunteer yourself, is why is this example not succinct? Why does this not meet our runtime requirements?
Well, we talked about this two times ago, but it's
Yes.
because W would be in like linear in C.
The W may not be linear in C.
Or C.
The W, the witness may be short. It doesn't necessarily have to be the length of C. The reason this isn't succinct is because in order for the verifier to verify it, the verifier has to run the entire circuit. The verifier has to plug the X and the W into the circuit and run every operation in the circuit, which would be linear in the size of the circuit.
Mm.
So yes, that's right. So even if you had just sent the simple proof of like the witness to the verifier, this would not be a valid SNARK because just running the circuit would take too long. So this part is what makes SNARKs really, really cool, is the fact that you can produce a proof that is even shorter in verification than the actual circuit itself and prove that the circuit will return 0. So this runtime requirement means that the SNARKs are succinct, which makes them useful on the blockchain where sending too much data is really, really costly. And then finally, we define the zero knowledge property, which is to say that these SNARKs can optionally satisfy this additional property of being zero knowledge, which means that the proof that is generated by the prover cannot reveal anything about W. And this is a formalized definition that we don't have to go into, but it's easy to turn a SNARK into a zk-SNARK. The key is to just inject some more randomness into the SNARK so that it's harder to tell what the proof is doing and what the proof is saying about the witness. All right, so now let's move forward to the applications. Last time we talked about two. First is rollups. Rollups are a way for L1 chains like Ethereum to handle a large quantity of transactions without having to produce a large quantity of blocks. Rollups make these sorts of transactions more scalable by batching them together. So by using zero knowledge proofs and Merkle trees, which we reviewed, Merkle trees, great refresher here. By putting these together, it's able to store just a little bit of information on the actual blockchain itself. It stores like the Merkle root, and it stores the proof that the rollup server basically constructs that says that the bundled transactions are correctly constructed, and then it submits it to the chain. Then the second application we talked about was confidential transactions, which is in the case that we want to guarantee privacy in the amounts transacted, but we don't want to anonymize the parties involved. We can replace the amounts in any given transaction with cryptographic commitments instead. So an example would be like this sort of transaction where the inputs originally, you could possibly tell that this is maybe 2 sigma paying me and then giving 2 sigma some change back. This could be turned into a confidential transaction by replacing all of the quantities involved with cryptographic commitment so that somebody looking at this transaction from the outside will not know how much 2 sigma has sent to me and how much 2 sigma is sending back to itself. Even though it is okay that they know who is sending it. Like I'm okay with people know that 2 sigma is paying me, but I don't want people to know how much 2 sigma is paying me, for instance. That's a use case for confidential transactions. This is another application of SNARKs because in this case, we could just create cryptographic commitments, but the big question is how can a miner on the blockchain check that this transaction is valid, check that the inputs, which is the 10 here, sum up to the outputs, the 9 plus the 1, if they do not actually get to see the numbers 10, 9, and 1. And we talked about how the zk-SNARKs are able to help because we can build a proof which shows that these properties are all satisfied. And then when we submit the proof with the transaction, the miner can verify the proof without ever knowing any of the numbers involved. Yes, Gabriel.
I was wondering, I guess, what are good, I mean, because I understand that confidential transactions, can be a good thing in general, but can't people just track, wallet balances over time? So I guess if it just if there's a low number of transactions, you could still sort of like probably deduce like how much like whatever token balance is in sort of these transactions.
So on a blockchain like Bitcoin, if Bitcoin were to have confidential transactions, the only way you could calculate a wallet's balance is by looking at all the unspent transaction outputs that have accrued to that address. And in a system like this, where all of the unspent transaction outputs have commitments as their quantities, you would not be able to know anybody's balance. It would just be impossible to know. Of course, on like a blockchain like Ethereum, that might be different. If like the smart contract is not built well, it could still leak the balances even if you have like, successfully encrypted the amounts in a transaction. But at least on like a blockchain like Bitcoin, which is sort of what this example is modeled off of, it would be impossible to tell at that point.
Okay, that makes sense. Thank you.
Great question. And last time we had talked about a special type of cryptographic commitment that has a additional property of additive homomorphism, which is that if you were to create a cryptographic commitment of one message, multiply it with a cryptographic commitment of a second message, that would be equivalent to creating one cryptographic commitment of the sum of those two messages, which is a useful property to define if we're trying to verify that sums of quantities add up to each other. And we could construct a Pedersen commitment by using a special type of group defined by like a large prime, where all the elements in the group are like some element G raised to different powers up until that prime. And we're hashing or committing using this cryptographic commitment scheme would include taking any elements and taking your message and raising it to the power of that message and raising it to the power of that randomness, and then producing a hash like that. This is an example of a Pedersen commitment because this commitment scheme satisfies the property that when you take two hashes together and you multiply them, then you get the hash of the sum of them. And that means that we could, in the previous example of the confidential transactions, not need a SNARK in order to prove that like the 10 equals the 1 plus the 9. We could just hash the 10 and put it on this side, and then hash the 1 and multiply it with the hash of the 9 and be like, aha, these are equal. So that must mean that they sum up to be the same thing. And so we talked about how we can send the right information to me, the recipient, so they can later use this confidential transaction to send money to other people, and then what the miner has to verify, and then the fact that we have these confidential transactions and these commitments does not necessarily mean that the entire blockchain has to be confidential. If at any point somebody like myself wants like a UTXO, the unspent transaction output, to be public, we can turn this confidential transaction into a public one by just sending the details of the transaction, sending the message and the randomness as metadata, and that will just break the confidentiality. But if that's what I desire, then I can send it. And in this case, the SNARK that we construct has to be zero knowledge, so it does not reveal anything about the amounts transacted. Okay, great. So that's a review so far. And now we're going to get into the two much more intense examples, which are also the more exciting examples of SNARKs. We're going to start with the Zcash. So last example was to produce privacy in the amounts that were transacted. This time, we want to guarantee anonymity for the transactions as well, so that both the parties and the amounts are hidden from any third-party observer. Zcash is a platform that has been built, a blockchain, an L1 blockchain that has been built to address this very issue. We're going to talk about how it uses zero-knowledge SNARKs. The main idea behind how to make these parties anonymous is to use shielded addresses in addition to these shielded transaction outputs. So whereas before, this first transaction is what we had produced from our confidential transaction technology, right? Like having these commitments here as substituting for the quantities, but not substituting out anything for the actual addresses. We're going to turn this into a transaction that looks like this, where we have a shielded transaction output, which reveals nothing about whether it's 2 sigma or it's me or somebody else. I'm just putting 2 sigma in parentheses here just so that we, as the people learning about this, can still identify which is which. But this would be a shielded transaction output that doesn't reveal anything about who, well, what address is underneath it. Then I would also have a shielded transaction output, which includes both the, like the amount being sent to me as well as like my address, but like it's been shielded so nobody can see it. And maybe when 2sigma receives the change, the 9 coins and change, maybe 2sigma wants that part to be public and doesn't want it to be shielded, in which case that particular transaction output can look like a very public, public blockchain record, which is just like the address is explicitly stated and that the value is explicitly stated. So this is what we're going to aim for. And we're going to talk about how exactly a zero-knowledge SNARK can get us there. And here, we've already answered one big challenge, which is like, how can the miner verify that like the inputs match the outputs if the amounts are all hidden? We use a SNARK to do that. But now the big question is, how can a miner check against double spending? Because if nobody knows that this transaction input was from 2sigma, well, what's preventing 2sigma from spending the same coin and multiple different transactions? If nobody can check that, like if the miner cannot check that, this was 2sigma that spent this coin. So this is where we're going to need SNARKs again. In particular, let's start with how we're going to generate this shielded address. We're going to use some hash function. Let's just call it h1 for now. You use some secret key and some randomness z as our seed, and we're going to produce a public key. Then a shielded transaction output, which we'll use as zk-SNARK as a shorthand, that is owned by this public key that has a certain value in its transaction output, like a certain number of coins, will be recorded on the blockchain as a coin. And this coin we're going to define as a hash. Specifically, it is this same hash function, but it is hashing all of these elements concatenated together: the public key, the value of the transaction, and some randomness rho, as well as additional randomness r. And so what's recorded on the blockchain is this coin rather than the actual transaction output value and rather than the actual address. So the blockchain is going to record a coin, and the randomness here is selected by whoever is sending this STXO. Right now, don't really know why the coin is built this way, but just know that the coin is including in the hash something that identifies the party sending it, something that identifies the value in it, and several sources of randomness. Then the second thing we have to define is a nullifier. A nullifier is another hashed value that uses a different hash function. It uses a hash function h2, and it takes as input the secret key of whoever is sending the transaction, as well as the randomness rho that that transaction center had picked for their coin. And that nullifier is produced and is going to be sent to the blockchain so the blockchain can record when each STXO has been spent. So when I was saying, how do we prevent double spending on a blockchain like this where nobody knows that, like 2sigma has spent a coin or not, the nullifier is a way to check if a coin that hasn't spent is being transacted a second time. And so we're going to now go into detail about how these two basically new tools, the shielded transaction output, the coin and the nullifier, are going to help us build this Zcash blockchain. So questions about how we've defined a coin and a nullifier so far?
Looks good. So Z, rho, and R, those are all sources of randomness.
That's correct. Yeah, they're all sources of randomness, and they're all randomness that the sender of this transaction output has picked for themselves. So now the blockchain will store these items. The first thing the blockchain will store is a Merkle root of the set of all coins that have ever been created before and submitted by anybody. This is going to be a massive set of coins, but the good thing about storing the Merkle root is the Merkle root is just one hash value. So that representation is going to be very short, like 32 bytes or something. The second thing the blockchain is going to store is a list of all the nullifiers that have been sent to it. This list cannot be turned into a Merkle tree. This list has to be explicitly enumerated on the blockchain. And then the third thing is the blockchain will store a set of transparent TXOs. So that's all the transaction outputs that people want to be transparent and do not want to be confidential. So like in that example of the 2sigma transaction, that's the second transaction output that 2sigma takes as change, maybe they want that one to be transparent. And so the blockchain will obviously store a set of transparent UTXOs like Bitcoin would have. So it just has like a second like second area over there that just stores the transparent part of the chain. And this part will store the confidential part. So really the confidential part is just the first two things. It's storing the Merkle root of all the coins, and it's storing an explicit list of all the nullifiers that have been sent to it. So then how does this all come together? Let's talk about that example with 2σ. 2σ knows first what the value of its input is. So V1 is how much money has going to send as input, which is like the 10 tokens. And it can generate row 1 and R1, which are its randomness. And so 2σ can use this information to create its coin. Coin 1 is, it's not creating the coin. This coin 1, let's assume, is already on the chain from when it received this V1 from a previous transaction. This coin 1 is again defined as the hash of 2σ's public key, the value 10, and these two sources of randomness, row 1 and R1. So how does 2σ take this amount of tokens and then create this transaction with them? What 2σ will first do is 2σ will help me generate a randomness row 2 and R2. Because 2σ is the sender of this transaction, 2σ is going to generate these. And using these two, 2σ is going to create a second coin. This coin has not been sent to the blockchain yet. This coin is just created in 2σ's private systems. So 2σ is going to create this coin 2, which takes as input first the private key, the public key that is mine. So this is my public key. It's going to take this value that is being sent to me, which is like 1 token, in this case, salary, and it's going to take these two sources of randomness right here, and it's going to hash them all together to produce this coin. And 2σ is also going to create a nullifier. This nullifier is going to be its secret key and the randomness that I used to generate its own coin. So what 2σ is preparing itself to do is to submit this new coin to the blockchain so that I can have a coin on the blockchain now, and 2σ is going to submit a nullifier that corresponds to its coin, so that when 2σ submits the nullifier, the blockchain will nullify that coin and not allow this coin to be spent again. So that's why the nullifier is noted with the subscript 1, matching up with this coin, and this coin is a subscript 2. So after 2σ has generated these two quantities, the coin and the nullifier, 2σ is going to build a huge snark. All right, and so what exactly is this snark going to contain? Remember, whenever we talk about a snark in any of these applications, I'm going to define for you the public information, X, the private information, W, and what the circuit, C, is evaluating. So in this case, the public information built into the proof is going to be the current Merkle root of all the coins, the nullifier that 2σ is preparing to send to the chain, the new coin that 2σ is going to send to the chain, and anything about the transparent transaction outputs, like the V3. The V3 is part of the transparent transaction. That can all be public. So because X is all the public information, all the transparent transaction information can be part of X. Now, what has to be private? The witness has to contain, obviously, 2σ's secret key, the randomness that 2σ used to generate its public key, the value of 2σ's initial balance, which is 10, 2σ's randomness, row 1 and R1. It's got to keep secret my public key so that nobody knows that I'm being part of this transaction. It's got to keep secret the value being sent to me, which is the 1 token, and it has to keep secret these sources of randomness that have been used to generate the coin and the nullifier. So then, based on these two sources of information, X and W, what is our circuit going to check? The first thing the circuit has to check is that 2σ is spending a coin that is on the chain. So it has to check that coin 1 is in the Merkle tree with this Merkle root. And so 2σ is going to have to produce a Merkle proof that this specific coin exists at a specific spot in the Merkle tree on chain. Because if 2σ does not have a coin in the Merkle tree, 2σ is not allowed to spend anything, right? So you have to check that this coin already exists in the Merkle tree. The second thing that this snark has to check is that the second coin has been constructed properly, that the second coin has been hashed using this correct construction, that the second coin wasn't just some random string of bits that has nothing to do with the values here. It checks that the coin is constructed correctly, and it checks that the nullifier has been generated correctly. It's also important here to note that it will also have to check that the nullifier has not been added to the chain yet. If nullifier has already been added to the chain, then the proof would also not work. Sorry, actually, no, that's not something that the snark checks. That's just something that the miner checks. So ignore that. The third condition that the proof has to check is the same thing that the confidential transaction had to check, which is that the values of all the inputs sum up to equal the values of the outputs, so that the 10 will equal the 1 plus the 9, and check that all these values that are part of the outputs are non-negative, so that the 1 and the 9 are greater than or equal to 0. And so based off of that, we're able to successfully do what 2 sigma needs to do in order to send this transaction out into the blockchain, with this shielded transaction output over here, and the shielded transaction output for me, and then a transparent part that is part of the change address. Questions so far about what 2 sigma is doing. Next we're going to cover what 2 sigma is going to send to the blockchain and what the blockchain is going to check. But for now, questions about how the proof is being generated and how the coins are being generated.
Yeah, so coin 1 was generated by some, it could have been generated by anybody, but the PK1 was 2 sigma's public key. And so that's how 2 sigma, and then like V1, row 1, and R1 were given to 2 sigma by whoever generated coin 1.
Yep, that's right. So V1
behind the scenes, like off the blockchain.
Yeah, so say whoever sent 2 sigma that coin 1, like say a client of 2 sigma paid 2 sigma, that client would have generated row 1, R1, and V1 and sent it all to 2 sigma.
Yeah, and then that client can no longer spend a coin 1 because they don't have 2 sigma's secret key.
Yep, that's right. Because in order to spend a coin, you have to produce the nullifier for it, and the nullifier requires a secret key. That's right.
Sweet. Okay, cool.
Bill, so PK2 is your public key?
Yes, PK2 is my public key. That's right.
I see. And V2 is the amount that 2 sigma wants to send you?
Yes, so that would be like the 1 coin in this example.
I see.
So this coin is basically mine. Like this coin is connected to my address now, whereas that coin was connected to 2 sigmas. So that is 2 sigma's coin. Coin 1 is 2 sigma's coin. Coin 2 is going to be my coin. Coin 2 is going to be something only I can spend on the chain. Yeah.
I see. Is there a reason for row 2 and R2 to be 2 separate random variables instead of merging as 1?
Yes. The reason why we need 2 separate random variables is because one of these 2 random variables is going to be used in the nullifier, whereas the other one is not. It's important that we have one source of randomness that is not going to be part of the nullifier, but we also need one source of randomness that is part of the nullifier. So we'll talk about like how the blockchain checks that this whole thing is valid, and part of the importance of having this randomness in the hash for the nullifier is going to be revealed to us then.
I see.
Great question so far. Yeah. And this second condition here is really important. I'll go over it a second time, which is like the proof has to check that the coin was generated correctly, and it has to check that the nullifier was generated correctly. So that means that it has to check that the nullifier is indeed the hash of the correct secret key. So it means that whoever is generating this proof has to have the correct secret key that corresponds to the public key from this coin, and that the person generating this proof has to know the correct randomness, row 1, that was part of generating that coin from before. So these together will show that whoever's generating this nullifier does indeed own this coin. And then the second coin has to be generated correctly, as we talked about. Other questions? Okay, so now step 3 is 2 sigma is going to send the nullifier that is produced. It's going to send the new coin, coin 2. It's going to send that whole big SNARK proof, and it's going to send whatever transparent transaction outputs it wants to the blockchain. Now, 2 sigma also has to do one other thing in the meantime, which is 2 sigma has to help me spend the coin later. So 2 sigma has to privately send me the value that 2 sigma is planning to send me. It has to privately send me the 2 sources of randomness that it has generated for this transaction, so that when I want to spend the coin later, I will have these values in mind so that I can create the nullifier and so on and so forth. Now, after 2 sigma has sent me all this information and 2 sigma has sent all of the coins and nullifiers and stuff to the blockchain, what is the miner on the blockchain going to verify? The miner is going to verify 3 things here. The first thing is the miner is going to verify that the nullifier that 2 sigma has sent it has not already been used. If the nullifier has been used before, it'll appear in the list of nullifiers on the blockchain. And if that's the case, the miner will reject this transaction because it'll know that somebody has already spent coin 1, because nullifier 1 only ever corresponds to coin 1. And if coin 1 has already been spent, 2sim is not allowed to spend it again. So the miner must verify that the nullifier does not yet appear in the list. The second thing the miner will verify is that the proof is valid. So basically that, the coin was generated correctly, the hash was generated correctly, that the coin exists in the tree, all the values sum up from the inputs to the outputs, and that all the values are non-negative, all those things. The proof will prove those things. And then finally, the miner will check that the transparent transaction part is valid, just like it would on the Bitcoin blockchain. Given that the miner has verified all of these things, the miner is going to do a few updates to its chain. If it's valid, it'll first add this new nullifier that's been sent it to the list. It's going to add this to the list of nullifiers on the chain so that now nobody can spend this coin again. It's going to add coin 2 to the Merkle tree. So that now coin 2, which is this new coin that's going to be mine, is now part of the chain. It's going to add the transaction that has been transparent this whole time to the UTXO set, just like on the Bitcoin blockchain. And of course, it's going to do some other overhead stuff, like it's going to generate the new Merkle proof and the new Merkle root and stuff like that. That'll all also happen. So how exactly is this whole thing anonymous? The reason that this whole thing ends up being anonymous is because to a third-party observer, when you submit a coin to the blockchain, nobody knows like what amount of money is in that coin, and nobody ever knows if that coin has been spent, because the coins are never ever removed from the blockchain. You just keep adding coins to this Merkle tree, but no coins ever leave it. And so nobody knows when a coin has been spent. The reason nobody knows when a coin has been spent is the only indication the coin is spent is the presence of a new nullifier on the list. But given a nullifier, nobody can trace which coin it corresponds to, because these hash functions are binding. And you cannot reverse engineer these hash functions. So because each nullifier doesn't reveal what coin it is nullifying, a third-party observer cannot tell which coin is being spent each time a new nullifier is added to the blockchain. So that means that I could have already spent my coin and you would not know about it. Maybe I haven't spent my coin, but you also wouldn't know about it. And so this is much stronger anonymity than before. Not only do we not know like how much value is in each of these coins, we don't know who the coin is intended to be spent by, because nobody knows the public key that has been hashed into it, and we do not know when it has been spent. So this Zcash platform is able to remove this ordering across time and remove all of these other idioms of use, because every single transaction ends up being confidential in the who's receiving the coin, the value being received by the coin, and when that person ends up spending that coin. Questions so far about this construction? Oh boy, either I lost everybody or this is just a very clear set of slides. One of them is more likely than the other, but I guess, yes, good call.
Yeah, I mean, for me, it's like, I don't have any specific questions, but I'm definitely gonna have to review this. So I just think more about it afterwards, but I don't have any specific questions.
Okay.
Bill, so
Mhm.
in order to verify that if one is not in the list of nullifiers, so does the miner have to store every single like nullifiers that have ever been generated?
Yes, that is correct. The blockchain is storing the entire list of nullifiers that has been sent to it already.
Let me see. That must be like a lot of nullifiers.
Yes, it is. It is a lot of nullifiers. I mean, one of my open questions that I haven't answered for myself is like, does this list ever get too big? Because like we had to make a Merkle tree out of the coins. Presumably every coin ends up being spent. So presumably every coin ends up having a nullifier. So this list of nullifiers seems like it'll become the size of the number of coins. And well, yeah, how's that going to work? So I don't know the answer to that, but it's something that I can look into.
With Bitcoin, it stores all of the UTXOs, right?
Yes.
which is
So,
like an ever growing list.
but the UTXOs are only the unspent transaction outputs. Once a transaction output has been spent, it's not stored in like a miner doesn't store it
It
anymore.
stops storing it.
Yeah,
Okay,
exactly. So the U in UTXO is unspent.
Gotcha.
In this case, because we don't know ever when something has been spent or not, the nullifier list will have to actually just grow forever.
I mean, I guess you can just hope that like computing power gets better and storage gets cheaper over time.
Yeah, I mean, the nullifiers thankfully are all like just like 32 bytes. They're not very large. So storing them isn't terrible. But yes, it'll grow over time.
Can you go over again why the nullifier is
Yes.
like 1-to-1 with a transaction?
Yes, so we're gonna go over that now. So let's talk in depth about the nullifier. The nullifier here that we've created using the second hash function needs these two arguments. Why does it need both the secret key and the randomness row? First, the secret key is hashed so that it only allows one party to ever spend this coin. And in particular, it only allows whoever has the secret key corresponding to the public key used in the coin. So remember, back when we constructed the coin and the nullifier, the coin was constructed using the public key, like 2-sigma's public key. So 2-sigma's coin is generated using 2-sigma's public key. And then when 2-sigma builds its nullifier, it uses its secret key. And in the proof that 2-sigma generates, one of the conditions it checks is that the nullifier was generated using the secret key that matches the public key of this coin. So that means that only 2-sigma can ever build a nullifier for its coin. Because if anybody else tries to build a nullifier for 2-sigma's coin, they're not going to know 2-sigma's secret key. And so the nullifier that they build is going to fail its proof. So that's how we know that this coin, like that the nullifier is corresponding to, has been created by, it has been owned by 2-sigma. The reason we need the second argument is because 2-sigma could have lots of coins, and you can't just have one nullifier that only takes as argument 2-sigma's secret key, because then 2-sigma can only generate one nullifier, period. It needs to be able to generate one nullifier for every coin that it owns. So this row 1 is the randomness that was used to create the coin. And so that every time 2-sigma generates a nullifier for a coin, this row 1 helps you uniquely identify which of 2-sigma's coins it is. If you removed this row 1, then 2-sigma would only ever be able to create one nullifier, which is just the hash of its secret key, and that would be bad, because then if 2-sigma has multiple coins to spend, it couldn't spend them all, which is why you need the second argument here, row 1. The reason you need the secret key here, what you might be asking, like, well, this row 1 is unique to every coin, so why don't we just use row 1 in the hash and not use the secret key in the hash? The reason we need row 1 in the hash is because 2-sigma is not the only party that knows this randomness row 1. The sender of that transaction also knows row 1. The sender of that transaction is the one who generated row 1. And so we don't want the sender of the transaction to be able to produce a nullifier for this either. So we need the combination of the two. We need this row 1 that helps us uniquely identify which coin is being spent, and we need 2-sigma's secret key so that only 2-sigma can produce this nullifier, so that we protect ourselves from the sender of the transaction nullifying the coin, and we protect ourselves from 2-sigma being locked into being only able to generate one hash function for one hash value for all its coins, and thus not being able to spend more than one coin.
So how do you cryptographically check if the nullifier corresponds to the coin, if like you're adding randomness to it?
So the proof is what checks it here. The proof checks that this nullifier is generated correctly with these properties. And so the proof is enough to ascertain that this nullifier is the only one that could be corresponding to this coin. So because like the witness here includes the information like row 1 and R1, the proof here is going to be able to check that like row 1 is used in this nullifier, row 1 was also used in this coin. It's going to be able to check that the secret key is used in this nullifier and the public key was used in this coin, things like that. So yeah, it's important here that the proof is very important because the proof is how the miner checks these things. The miner never actually does anything with the nullifier and the coin. It doesn't like put them in put them under a magnifying glass and like examine them itself. The miner just accepts the proof and has to trust the proof. The proof is the one doing the examining that the coin and the nullifier correspond to each other.
So we don't know what the proof looks like, right? Like, or you haven't talked about that.
To actually build the proof is what the next half of the talks will be about. To actually build that proof. But for now, just imagine that the proof is one very long string that the miner will accept, and the miner, when it decides whether this proof is valid or not, the miner does know some things. The miner knows the public information, right? And the miner also knows how the circuit was built. So the miner can verify that this proof is valid for this circuit. So if I try to create a proof, but it was for some random circuit that doesn't actually do these checks, the miner would still know that because the miner would realize, this proof does not correspond to the circuit that I want it to correspond to. So then the miner can reject a proof that isn't checking all these things. Great questions. So yeah, sorry, going back to the nullifier slide. So the nullifier requires both of these arguments because first, the nullifier needs the secret key. So so the nullifier cannot only have a secret key. If the nullifier was generated this way, that would be bad. Because if it only uses a secret key to generate, then one party can only ever spend one coin ever, because there's no way to differentiate between all the different coins the party might own. There's only one secret key argument here. So the nullifier cannot just have this one argument. And the nullifier cannot also just have one argument, which is the row, the randomness, because the STXO sender knows row, and the sender will then know when the coin is spent. The sender could also nullify the coin themselves. So the nullifier has to have both of these arguments as input, has to have the secret key and the randomness row in order for it to satisfy what we want it to do.
Hey, Bill, what do you mean by sender? Isn't the sender here like 2 sigma or?
Yeah, so for coin 2, the sender is 2 sigma. For coin 1, the sender is like 2 sigma's client that sent it to 2 sigma. So in the end of the day, 2 people in the world know each row and each R. The 2 sigma client and 2 sigma know row 1 and R1, and then 2 sigma and I will both know row 2 and R2. So the fact that 2 sigma will know what my row is when I want to spend my coin, that's why I cannot just use row in my nullifier. Otherwise, 2 sigma will know about it because 2 sigma knows what row is.
I see.
So let's talk about a possible attack, like one vulnerability that still exists in the system. When 2 sigma creates coins, maybe 2 sigma has to send me, salary every month or something. When 2 sigma creates 2 coins to send to me, 2 sigma could be malicious and decide I'm going to use the same row. I'm going to use the same randomness for both coins. If 2 sigma uses the same randomness for both coins, then the coins are going to have the same nullifier. And that means I cannot spend both these coins because once I submit one nullifier for the first coin, if I try to submit a nullifier for the second coin, the blockchain is going to check and be like, oh no, this nullifier already exists in our list. But it's not because I spent the second coin, it's just because 2 sigma use the same randomness for both coins. So that is still a possible attack vector, which is that if one party is trying to send the other party multiple coins, they could try to use the same randomness for all the coins being sent. So what's the solution to this attack? The solution here is we could add a requirement to our SNARK. We could add a requirement that our randomness row is generated using the Merkle tree position of that coin, so that way the randomness, like say, it can be as simple as appending the Merkle tree position of the coin to the end of that string row. That string row is like a random string. We append the tree position of the coin to the end of row. And that way we ensure that every row that is generated is unique to the coin. That can be an additional argument that can be an additional check that the circuit uses. So the proof will check this additional thing. And this will prevent 2 sigma from using the same row for 2 coins that it sends to me.
That's a cool solution. It makes me wonder, to what extent does Zcash have support for like smart contracts? Or like that those types of like ripple down, like being able to use these coins for doing things as opposed to just transferring them around?
So great question. I think Zcash, to my knowledge, has just the same functionalities as Bitcoin has, which is a script public key and a script sig for each transaction out, like UTXO. So every unspent transaction output will have with it a script public key, which is just a like 1/2 of a programming script that says how it can be spent. And then whoever ends up trying to spend it, like me, for instance, I would give it a script sig, which is like the other half of this programming script that tells it how to spend it. And so you can control how the coin is spent under what conditions, maybe with a multi-sig, maybe with you know, some time like time lock or something. But it's very, very basic because the scripting language in Bitcoin uses a stack machine, which is Turing complete, and it is not nearly as expressive as like the state machine that Ethereum has. So the short answer is Zcash is like Bitcoin. It is not very, very good at building anything smart contract related. Zcash was built back in the era of like Bitcoin before Ethereum really took off.
Yeah, gotcha. And then I guess like a related question is to wonder whether you could build a Zcash Ethereum like blockchain, or whether like there's some zk-SNARK technical limitations that would make it difficult.
I don't know the answer to this question, but I imagine that you definitely could, because all the other things that are really being sent in Ethereum smart contract that are like updating state could all be included as a SNARK. I think the concern is that it would, maybe the SNARK technology is not there yet, because the proofs could just become massive when you're not just tracking the balances of these coins, but you're tracking on tons of these other things.
Okay, sweet, thanks.
Yeah, but we're going to talk about how zk-SNARKs have been used on these chains when we get to Tornado Cash. So let's finish up Zcash by talking about some of the pros and the cons. Zcash is great because it is completely private and it is actually provably secure. So like all these proofs, as long as they're generated correctly and as long as the miners are, you know, honest, will protect all the identities of the people sending and all the quantities being sent. And Zcash also supports the transparent transactions too. So if you as a user want to interact with some exchange or some system that needs to know your identity, like KYC systems, you could still do so because you could use transactions that are transparent and or interact with them that way. The cons of Zcash are, first, there is a lack of adoption. It requires an L1 chain. It can't be built on an existing chain. So if people want to use Zcash, they can't, you know, use Ethereum at the same time. And it's also not coin agnostic. It doesn't protect all coins. It only protects its own coin, the coin on its blockchain, which is Zcash. Just like Bitcoin can't support any other tokens, Zcash also can't support any other tokens. And the other con about Zcash is that it faces a lot of regulatory pressure because the government does not like it. The government does not like the fact that it is completely anonymous. And so that pressure prevents lots of exchanges like Coinbase or Binance from accepting Zcash deposits because of the KYC concerns. So as a result, Zcash doesn't get as much adoption because it's not able to integrate with a lot of these exchanges that the not private coins are able to. I see some questions in the chat.
Sorry, I was just linking Cole to a like an L2, like a privacy focused rollup that it looks like it does actually use zk-SNARK tech behind the scenes.
Yes, Aztec is a recent innovation that is on Ethereum and uses the zk-SNARK technology. Great resources. Questions about Zcash? If not, we are going to move on to the last example. And this example is one that is my favorite because it's one that we can all, you know, feasibly use if we wanted to today, Tornado Cash. Tornado Cash is, if we haven't like heard of it already from all the like the hacks and the thefts in the past couple months, let's talk about it formally. Tornado Cash is a zk-SNARK based mixer on Ethereum. Earlier, 2 weeks ago, we talked about what a mixer does. A mixer just takes your transaction outputs and then stores it in some sort of smart contract or something and allows lots of people to send in their money at the same time so that when you withdraw your money, nobody knows if you withdrew your money per se or any of the other people's money that have been sent in the meantime. So it mixes all your money up. And it's pretty basic to implement, but like we had said before, it is not a very good way of ensuring privacy because a lot of the idioms of use are still valid when you examine a mixer. Well, let's talk about how a zk-SNARK-based mixer is better. So first, instead of like how the previous mixers we defined use an off-chain form, Tornado Cash uses a smart contract on Ethereum. And now we're going to talk about like what exactly is the way to use Tornado Cash and how is it built. And we're going to see that Tornado Cash is built very, very similarly to Zcash. It's as if we just took Zcash and made it like a coin agnostic mixer on Ethereum instead. So users can add inputs to the smart contract or deposits to the smart contract without specifying where that money needs to go on the other end. And then users can withdraw money from the smart contract without specifying what the input it corresponded to was and withdraw it to any desired address at any time. The way the Tornado Cash system is set up, a very simple diagram over here, looks like this. And immediately we see a lot of resemblances to Zcash. We see coins, we see a Merkle root of coins, we see the nullifier list. So immediately, like if we were to take a step back and think about it, okay, how is the system likely to work? Okay, it sounds like the way the system is going to work is when users deposit money, they deposit coins. And then when users withdraw money, they send nullifiers. And the smart contract checks that the nullifiers aren't in the list yet. They check that the coin's in the Merkle root. They're going to check the proof, and then they're going to send the money to whoever's withdrawing it. That's like the very basic high-level intuition. But now let's talk about like exactly what is going on here. In this smart contract that's visualized here, first thing the smart contract is storing is its treasury. Notice that this treasury is denominated in one token. Each treasury, or basically each segment of Tornado Cash, can only store one token. So the DAI treasury only stores DAI. And so when you try to send in your DAI to this Tornado Cash contract, you will only be able to mix up your DAI with everybody else that's sending DAI. You will not be able to mix up your DAI with people that are sending like Ethereum or anything like that. So that's the treasury. The treasury stores how much DAI is in the contract right now. It's going to store the coin Merkle root, which is 32 bytes. It's just going to store the Merkle root, just like Zcash did. It's going to store an explicit list of all the nullifiers that have been sent to it, which is one entry per spent coin. And it's going to store a few pieces of metadata that are important, which is like the next spot on this tree, this Merkle tree, and the Merkle proof for the next spot on the tree. So say that right now there are 300 DAI in the treasury because there have been 3 coins deposited, coin 1, coin 2, and coin 3. These are the leaves of this Merkle tree. And this Merkle root is what is being stored here. So then 4 is the index of the next position. I'm sorry that the index isn't starting at 0, but it is what it is. And so the Merkle proof that is being used, that is being stored in this contract, is the Merkle proof corresponding to where the next coin would be stored. Questions about what you see on the screen right now. I'm going to talk about how people send in coins and how people withdraw coins in a second. Okay, so to deposit 100 DAI, say I want to send my DAI to Tornado Cash so that then I can withdraw it from the other end anonymously. I will choose some randomness, K and R. This is very resemblant to Zcash. I'm going to call this combination of K and R a note. I'm just going to call it a note, but it's just two random variables. I'm going to create a coin from this node. The C4 is going to correspond to the hash function of K and R. In this case, notice that this is different from Zcash because we're no longer hashing our public key. We're no longer hashing the value of the 100 DAI into this because the value that we're sending and our public key are public on Ethereum. There's no point in trying to hash them here. But we're going to just hash these 2 sources of randomness, which are just like the 2 sources of randomness from the Zcash example. We're going to then put our new coin, C4, into our local copy of the Merkle tree. So remember that Merkle tree we had a moment ago, which had 3 coins in it. We're going to put coin 4 in the next position in the Merkle tree. We're going to then compute not the Merkle proof of our position in the tree, but we're going to compute the Merkle proof of position 5, which is like the next empty position of the tree. And then we're going to send our 100 DAI, we're going to send our coin, and we're going to send this Merkle proof that we've built to the Tornado Cash smart contract. It's a little bit cryptic. Like, why are we computing a new Merkle proof? All of this is just so that the Tornado Cash smart contract can update itself and be ready for like whichever next user wants to use it. So then the contract will compute the new Merkle root given this coin 4 that gets added to it, It'll verify this Merkle proof is correct, and then it'll update its own state so that it now looks like this. It's going to update its treasury to accept the new 100 DAI. So now it's 400 DAI instead of 300 DAI. It's going to update its Merkle root because now it has coin 4 in the 4th position. And so its new Merkle root is going to be replacing the old one here. It's going to increment next to 5, 5 being the next empty slot in the tree. And it's going to take our Merkle proof for position 5 and store it here as its metadata now. This is the updated smart contract state. This is all I have to do if I want to deposit my DAI. Now, remember a moment ago in Zcash land, we were talking about how nullifiers were going to be produced. Nullifiers were going to be produced with a secret key and randomness. Well, that can infer that now, if we want to withdraw some money from the Tornado Cash, we're going to probably do something similar. So say that somebody else comes along and wants to withdraw coin 3, not coin 4, the one that just got deposited, but wants to withdraw coin 3 from Tornado Cash, that 100 DAI coin 3. How is that going to work? First, they're going to use the note that was built for coin 3, so that K prime and R prime that were used to generate coin 3, and they're going to compute a nullifier, which is a new hash function, H2, of the first part of the randomness, the K prime. So just like in the Zcash example, where we used rho to generate our nullifier, we're using K prime here to generate the nullifier for that first coin. Then whoever trying to withdraw this coin is going to build a zk-SNARK. In this proof, the public information is the current Merkle root of the Tornado Cash smart contract. It's going to be this nullifier that you built, and it's going to be the withdrawal address that you want the money to be sent to. The private witness is going to be the randomness K prime, which we got to keep secret, the randomness R prime, which was also important for generating the coin, so we also got to keep that secret. So this is our note over here, right? The previous note for C3. The private witness is also going to include the coin itself because we don't want that to be revealed to people. And it's also going to include the Merkle proof of this coin. So proving that this coin is in the Merkle tree that is being stored in the smart contract. These are all things that cannot be revealed to people. These are all things that can be revealed to anybody. Then the circuit is going to check 3 things. It's going to first check that this Merkle proof is valid for coin 3 at position 3 in the Merkle tree. The second thing the circuit's going to check is that coin 3 was indeed constructed using a hash function that used K prime and R prime in it. So it's going to check that whoever's building this proof knows K prime and R prime, and thus was the one that it could have basically has the rights to coin 3. And then it's going to check that the nullifier was generated correctly as the hash of K prime. This proof ultimately demonstrates that whoever is trying to withdraw this money both knows what the coin it is that they're trying to withdraw, knows the randomness that is like the private key of the coin, and has produced like the nullifier correctly. Now, one very, very important thing here that I've highlighted in red is this withdrawal address. Technically, this proof could work without a withdrawal address. This proof could work without a withdrawal address because withdrawal address is actually not used to check any of these things. It doesn't matter who you're withdrawing to. All these checks can be done without the withdrawal address. Can anyone venture a guess why we still need to include a withdrawal address when we're generating this proof?
That's like, I mean, there needs to be a withdrawal address to send the coins to, but I guess the alternative is to specify the withdrawal address separately from the proof. And
Yeah,
the question is why we don't do that.
Yeah, we could just send the withdrawal address not as part of the proof, because the withdrawal address is going to be public anyways. Like once Tornado Cash sends money to an address, everybody on the Ethereum, anybody with an Etherscan can see the withdrawal address. But why do we have to include it in this proof if it's not going to be used in any of the circuit checks? The answer is, if we don't put the withdrawal address in there, anybody who sees our proof could use it for themselves. And so a miner on Ethereum can take this proof if it didn't have a withdrawal address in it and use it for itself and front run us. And so building a withdrawal address into the public information X means that this proof is now unique to our withdrawal address. The proof that is being generated, this string of bits, is now binding to this withdrawal address. If somebody had tried to generate a proof with a different withdrawal address, that proof would look different than this one. And so this proof now only works for our withdrawal address. If the miner tried to front run us, the Tornado Cash smart contract would reject that proof because it would notice that that withdrawal address is not the same as the address that is trying to actually withdraw the money from the smart contract. So this withdrawal address, because we specify it as ours, is going to protect us from being front run because our proof is now only going to work for our address, even though our proof is not using the address in any of these checks.
Cool,
So,
yeah.
The last step here for us, if we're trying to withdraw money from the smart contract, is we will send our nullifier, and we're going to send our proof, and we're going to send our withdrawal address to Tornado Cash, where we want the money to go. And now what does the Tornado Cash contract do? It'll check a couple things. First, it'll check that this proof is valid, just like what every one of these examples has been doing. It checks that the proof is valid. Second, it checks that the nullifier is not already in its list, which is the same thing as Zcash. And afterwards, once it's checked these two things, then it'll add the nullifier to the list. It'll send the 100 DAI to the withdrawal address. And now coin 3 can never be spent again because the nullifier that corresponds to it is in the list. If anyone else tries to spend this coin, they're going to have to send the same nullifier, and then the smart contract is going to say, this nullifier is already in the list. You're not allowed to spend it again. And so this is the updated contract state after this is all done. This treasury now has 300 DAI again instead of 400 because 100 has been withdrawn. This Merkle root has not changed. The coins in this Merkle root have not changed because this coin is never pulled out of it. This coin is never removed. So nobody on the outside world knows which coin was the one that got spent. This nullifier got added to the list, and everything else stays the same. So in this case, Tornado Cash is able to withdraw your money to whatever address you want, and nobody knows whose money it was that you withdrew because nobody can link this nullifier to this coin. Nobody knows which coin this nullifier corresponds to. Only the proof knows that. And when the Tornado Cash contract verifies the proof being zero knowledge, hides that from the Tornado Cash contract and thus hides it from the world. So in this way, Tornado Cash is able to at least protect, it's a better mixer than the ones we discussed before, because when you withdraw money from Tornado Cash, people do not know whose money you withdrew from the entire history of everybody that has used Tornado Cash. So your anonymity set is now not just like 40 people. Your anonymity set is everybody that has ever used Tornado Cash ever. And somebody from the outside will never, ever be able to definitively say if money somebody put in Tornado Cash is ever withdrawn. So say you you stole money from like a bridge and now you put it in Tornado Cash. Nobody will be able to know the money that you're putting, everybody will be able to know that this thief is putting money into Tornado Cash, but nobody's going to be able to know which withdrawals from Tornado Cash correspond to the money that the thief put in. That's what makes Tornado Cash better than all the other mixers out there that don't use zk-SNARKs. But of course, it is not as protective as Zcash because Tornado Cash is just a zero knowledge and an anonymous smart contract on an otherwise public blockchain. Everything else on Ethereum is public. So Zcash is still more private because it's an entire L1 that is like completely private and anonymous. But Tornado Cash is a very, very cool and useful innovation on the Ethereum blockchain that uses these zk-SNARKs. Questions about Tornado Cash?
I have a question. So why does an observer does not know which coin is spent? Like I would just like try to spend that coin. If I failed, I would probably know that the coin is spent.
The reason you wouldn't be able to try to spend the coin is because you can't produce a valid nullifier for the coin.
Oh, I see.
Because the nullifier needs to include the randomness that was used to generate the coin in the first place.
I see.
And so if you just try to send a random nullifier to the smart contract isn't even going to tell you whether it's in the list or not. The smart contract is going to say your nullifier does not correspond to like any coin in this like tree period. So we're just going to reject your proof there.
I see. Makes sense.
Yeah. So the only way you could even try to spend a coin is if you know the randomness behind it.
Makes sense.
So at the end, you were comparing the zk-SNARK Tornado Cash versus traditional mixers. But for traditional mixers, if a hacker sent money into the mixer and like potentially they would pull it out, but there still would be no way to know whether or not the hacker pulled the money out of the traditional mixer, right?
I think the reason that you could know that a hacker pulled their money out, I think, is because that the communication had to happen in some sort of off-chain forum. And I guess like when the hacker tries to pull the money out, they're gonna have to communicate something about they're gonna at least have to, I think they're gonna at least have to tell you what like timestamp, what batch of inputs it came from. So
Okay.
like if I sent him money at T0 and I try to withdraw money at T1, I think I like in the traditional mixer example, I'm gonna at least have to tell you that like the money came from T1. Sorry, came from T0 or something like that.
So there's, you can like perfectly map it, but like the amount of information you have is like, there's a lot less mixing going on, sort of. Do you know when Tornado Cash switched to the ZK approach?
I think it was in like 2021 or something. I know
Okay,
I
cool.
know they didn't start out this way. I know that they built it in more recently. I don't remember if 2020, 2021 or something, but it is recent. Of course,
Sweet.
like we have heard of instances since then where they've still been able to trace things through Tornado Cash. Tornado Cash isn't perfect. The big reason it's also not perfect is because like if you have really good chain analytics, you can still tell if like a humongous sum of money, like several $1 million of money, like goes into Tornado Cash and then aggregates out the other end or something. That's still possible because it's not, the entire chain isn't private. There's just this one smart contract.
Yeah. No, that's really cool how with the ZK, it's like, it mixes you with everybody from the entire pass, even if you like you just deposit and instantly withdraw.
Yep.
I still, one question is, can you explain again why you need the Merkle proof of the next empty slot?
Why that is used? I think that is honestly just for convenience. I think the
to
Tornado
speed up
Cash
computation
contract,
or something.
yeah, it doesn't want to do it itself. The contract doesn't want to build this proof itself, so it just asks each new user to build it because it's faster for the contract to verify the proof than to build it itself. So building the proof off chain, having each user build the proof off chain for the Merkle tree is like more efficient.
Okay, cool.
All right, so that brings us to the end of this week's lecture. So we didn't actually get into the building a snark part, but I promise you next time we'll start building our snarks. I know that like from all the anticipation, all these applications have given us, you might think that building a snark is going to be super exciting and fun, but I'm going to tell you right now and preface that next week when I send the slides out, please start looking at them beforehand because building a snark is going to be really, really mathematically rigorous and like difficult. So be prepared for next week's to not be all like fun and like application-y. It's going to be a lot of math. So I will end it there. Thanks everyone.
Sweet. Thanks so much, Bill. That was awesome.
Thanks so much, Bill.
Thank you, Bill.
So